Welcome to the flock. Let's dive on into this review of electrochemistry, where we're going to go over oil rig, anox eta red cat, drawing galvanic cells, and calculating for cell potentials. Stick around to see how it's done. The bare basics of electrochemistry is first identifying which chemical gets reduced and which chemical gets oxidized. In other words, which one gains electrons and which one loses electrons, respectively. The first thing we need to do is assign oxidation state values to each chemical represented in the reaction, and see if there is a change in charge from the reactant side to the product side. Only then is it considered a redox reaction, if there's a change in charge. So looking at the following chemical equation, we see that we have something with a +2 on the reactant side going to 0 on the product side. I know that that's a 0 oxidation state because iron is by itself. In order to go from +2 to 0, if you think about that on a number scale, we would have to be going backwards. In order to go backwards or towards the negative side of the scale, we would need to be adding things that are intrinsically negative, i.e. electrons. So by adding electrons, we can make a positive number become more negative or go towards 0. Therefore, we know that the iron must have gained electrons. And if it gained electrons, we're going to apply the rig part of our oil rig mnemonic, meaning that the iron is the part that gets reduced, hence the R. Reduction is gaining electrons. So iron here is the one that gets reduced. Whereas if we want to know which one gets oxidized, at this point it's process of elimination. We know that the only chemical left over is the cobalt, so that must be the one that gets oxidized. But let's make sure we understand why. On the reactant side, the cobalt is a 0 oxidation state, and on the product side, it's +2. So when we compare the reactants to the product, we see that it becomes more positive. If you become more positive, that means you must have lost something that was intrinsically negative, i.e. electrons. And if you lose electrons, you're looking at the oil part of our oil rig mnemonic, because oxidation is losing electrons. That's why we know cobalt is the one that got oxidized. The next mnemonic that we need to apply is the anox eta red cat in order to decide which one is the anode and which one is the cathode in this scenario. We know that anox means that the anode is the one where oxidation takes place. So we already said that cobalt is the one that gets oxidized, therefore it must be the anode. And if anox ate a red cat, we know that where reduction takes place, that is the cathode. We already said that iron is the one getting reduced, therefore it must be the cathode. This also means that the electrons will flow from the anode to the cathode, so from cobalt to iron, meaning that iron will gain mass as the reaction proceeds. And cobalt, of course, will lose mass, respectively. Now that you've seen me try it, go ahead and pause the video here and make sure that you can also identify which species gets oxidized, which one gets reduced, and which one is the anode, and which one is the cathode. Ready? Go. Let's see if you got it right. Hopefully that's the answer you got, and if so, awesome job. Let's move on to the next concept. Before we write out half reactions and then use those to draw a galvanic cell, remember that batteries are essentially an enclosed galvanic cell, where we have a connection between the oxidation and reduction parts of a redox reaction literally inside a battery. And when we connect both ends on the top, we are causing the connection between the oxidation and reduction half of the reactions and allowing the electrons to flow through it and light up our light bulb, or activate a child's toy, for example. Heavens, I go through millions of batteries to activate all of my daughter's toys. Unexpected parenting expense. By applying the same methodology we used prior to identify which chemical gets reduced and which one gets oxidized, we can then split up one chemical reaction into its half reaction counterparts, the reduction half and the oxidation half. Let's give this one a try. On the reactant side, we see copper is bound up in an ionic bond with chlorine. If we do reverse drop and swap, that 2 will go up here, and we have +2 for the copper, and we know chlorine's charge is -1 from the periodic table. However, on the product side, we see that copper is alone, so it would be given a 0 charge. On the reactant side, magnesium is alone, so it gets the 0, and on the product side, it's bound up with chlorine. Again, doing a reverse drop-in swap, we see magnesium is +2, and chlorine is still -1 from the periodic table. We know that since the chlorine didn't change from either side, it's a spectator ion, so we don't care about it. We're not going to use it in the half reactions or do any calculations with it whatsoever. We're going to pretend that it doesn't exist. Now if we compare the copper from both sides, we see we went from +2 to 0. That means we must have gained something that's intrinsically negative, i.e. we gained electrons. As we saw before, this applies to our RIG scenario, therefore copper is going to be our reduction half reaction chemical. We're going to start by writing copper +2 plus some number of electrons, because in reduction half reactions, the electrons will always be one of the reactants. That's going to come together to form copper 0 charge. Now the next question you need to ask yourself is how many electrons does it take to go from +2 to 0 charge? Hopefully you know that answer should be 2, because 2 minus 2 gives us 0. Now for the magnesium. When we look at magnesium, we went from 0 to +2 charge. That means we went from something more negative to something positive, so we must have lost something intrinsically negative, i.e. electrons. That applies to our oil part, therefore we know that magnesium is going to represent our oxidation half reaction. For the oxidation half, we're going to write magnesium 0 from the reactants over here, and I'm going to line up my arrows. I do this every time. It makes it easier to see what side the electrons are on when everything is said and done. Then we know we needed to lose some number of electrons, and so we're going to write a space for the number of electrons we lost on our product side. And we're also going to add magnesium +2 down here. Now to go from 0 charge to +2 charge, hopefully you see we would have needed to lose 2 electrons. Well, those are our 2 half reactions. We also want an overall reaction of what's going on. We see that our 2 electrons cancel because they are the same, and now we can write our overall reaction as follows. Copper +2 plus magnesium 0 charge together forms copper 0 charge, or copper not, plus magnesium +2 charge. And that's the big picture overall what's happening in this redox reaction. Now let's take that information, these half reactions specifically, and use them to draw a galvanic cell. For any galvanic cell, the first thing we need are 2 containers. We already know that the half reactions are as follows, and so I wrote those below our containers. That means that we're going to need a piece of copper in our right-hand reduction container, and we're going to need a piece of magnesium in our left-hand oxidation container. We'll need a wire to connect the 2 of them as well, so that the electrons can travel from one to the other. But which direction are the electrons going to travel? We need to use our an ox ate a red cat mnemonic. We know that the electrons will always travel from the anode to the cathode. We know that the cathode must be the one that gets reduced, so copper. Therefore, the anode must be magnesium. And if the electrons are traveling from anode to cathode, then the electrons in this case would be traveling from magnesium to copper. As the reaction proceeds, the electrons are going to accumulate negative charge on the copper, so the copper is going to become increasingly more negative. And as that happens, the magnesium will be increasingly more positive. The solution that the copper is submerged in is the copper chloride. I know that because the whole reaction previously had chlorine as the spectator ion. Remember, we didn't care about it then? We care about it now. And on the oxidation half reaction, my solution is magnesium chloride, again from the previous given equation. Remember that copper chloride is an ion, so it's going to be floating around in aqueous solution in its counterparts. So copper +2, chlorine -1, chlorine -1. As the copper metal here becomes more negative, this copper here in solution is going to be attracted to that negative more strongly than it is attracted to these chlorines. So it's going to break off those chlorines and stick to the copper metal that's becoming more and more negative. Meanwhile, these chlorines are going to be very attracted to the positive magnesium that's forming in the oxidation half reaction. So they're going to travel up through the salt bridge into the other beaker and be attracted to the magnesium. And this is why, as the reaction proceeds, copper will gain mass, while the magnesium will lose mass as it loses its electrons. Remember that you always need to show that salt bridge connecting the two half reactions. That salt bridge is literally what allows the cations to flow to the cathode and the anions to flow to the anode. Now that you've seen me try it, go ahead and pause the video here and see if you can figure out the half reactions and draw the galvanic cell for the following chemical reaction. Ready? Go! Let's check your answer. Hopefully that's the answer you came up with. If not, make sure that you pause, reanalyze, make sure you understand what you got wrong and why. If not, you can always comment below and I'll be happy to help. Here's just a quick break application question before we move on to calculating for cell potentials. Why do car batteries die? And what happens when you jumpstart a car battery? Inside a car battery, which hopefully we all have seen at one point in our life, there are metals. There are the anodes and the cathodes, and they're surrounded or submerged in a solution of sulfuric acid and water, which is, by the way, why you should always wear goggles when you jumpstart a battery. You're literally adding electricity to an entire cube of sulfuric acid. Heavens forbid that explodes and gets in your eyes. Anyhow, when the anode and the cathode are this close together in solution, what happens sometimes, especially in hot areas like Arizona or the West Coast in general, is that the water will evaporate from the battery over time. And as that happens, the anode and the cathode inside the battery then have the ability to grow towards each other and touch. Remember that the cathode is gaining mass. It's literally gaining size as the reaction continues. So as it gains mass, it's going to get closer and closer to touching the anode. And once the cathode and the anode touch, there's no way for us to harness the power between the anode and cathode. Remember, this is where we gain our power. Instead, they're just transferring electrons immediately without giving us the ability to force the electrons to flow where we want them to. So jump-starting the battery forces the electrons back in a direction that we can find useful, i.e. starting our car again. Also, sometimes all you need to do is add a little bit of water to your battery to fix the problem and make it work again. Life lessons with Lisa. Now let's calculate for the cell potential given a chemical redox reaction. As usual, we need to figure out which one gets reduced and which one gets oxidized. In this case, we're going to look at zinc first. Zinc starts with a +2 charge, we know that from reverse drop and swap, and it ends up with a 0 charge. Since it went from something positive to something more negative, we know that it must have gained electrons. So it's going to represent the reduction half. And that would be zinc +2 plus some number of electrons forms zinc no charge. To get from a +2 charge to 0, of course we need to add 2 electrons. Let's look at lithium next. Lithium starts with a 0 charge because it's by itself and ends up with a +1 charge. I know that from reverse drop and swap because nitrate here, a polyatomic ion, has -1 charge. There's also one down here that I can put up here. Likewise, on the reactant side, this nitrate has a -1 charge. In other words, we don't care about the nitrates. They're spectator ions. We don't care. Pretend they're not there. All right, so let's draw the oxidation half then in terms of lithium. Lithium is starting with no charge. I'm aligning those arrows again, and it loses some number of electrons to become lithium +1 charge. Of course, to go from 0 to +1, we must have lost 1 electron. Let's make sure those electrons balance by multiplying this bottom oxidation half by 2. The 2 distributes through and we end up with 2 lithiums, 2 electrons, and 2 lithiums here. Now we could see that our electrons would in fact cancel correctly. Now let's take a look at the cell potential voltage, which I gave you here in the table, but you would need to look up online or in the back of your textbook. We're going to follow the reaction as written. So what we see is the zinc plus 2 electrons going to zinc 0 charge is written the same way we have written our half reaction. Therefore, we're going to keep the negative 0.76 as is. However, when we look at our lithium reaction, we see that the way we have written it is exactly reverse of what was given. Since that's the case, we need to flip this one around, and when we flip that one around, we also flip the sign of the number. So instead of negative 3.04, we now have positive 3.04, and that's the value we're going to use up here. Now all that's left to do is to add these two values together in order to calculate our cell potential value in volts. And our final answer is 2.28, and that's of course in volts. Think you can do it? Let's try it. Go ahead and pause the video and see if you can calculate the cell potential for that redox reaction. Ready? Go! Let's check your work. Hopefully that's the answer you got, and it might be a little different than what you saw in the previous video. We always were striving for that positive answer if we weren't given a specific reaction. In this case, we were given this reaction and we need to follow it as written. And since we did so, we ended up with a negative voltage. That basically just means that this galvanic cell would be non-spontaneous. It wouldn't really want to happen all on its own. So to have a functioning battery, we would have a spontaneous cell potential, and that would have to be positive. It's okay if you end up with a negative value, as long as it's from an equation that was already given and you were following it as written. In this review lesson, we went over that separating reduction and oxidation half reactions allows us to harness the electron flow and use it as electricity, which of course we measure in volts, thanks to Mr. Volta. Electrons will always flow from the anode, that's the electrode that has oxidation taking place, to the cathode, that's the electrode that has the reduction taking place. Remember the mnemonic oil rig. Oxidation is losing, reduction is gaining. Electrons, that is. And an ox ate a red cat. Anode is where oxidation takes place. Ate a reduction is at the cathode, cat. Galvanic cells are literally drawn as two half reactions, and we're always going to connect those two beakers or those two containers with a salt bridge, and also, of course, a wire connecting the two electrodes. And lastly, we can use cell potential tables either online or in the back of your textbook to find voltage values assigned to specific half reactions and determine the voltage that could be created from a redox reaction. When you do so, make sure that your electrons do cancel. The reduction half is always going to have those electrons on the reactant side, and the oxidation half is always going to have the electrons on the product side. If you do need to multiply the equation in order for the electrons to balance, make sure you do not multiply the voltage values by that same value. We leave those alone. The only thing we change about the voltage values is whether it's a positive or negative symbol according to the reaction as it is written. Before you go take that test on electrochemistry, make sure that you can answer these questions with ease. Comment your answers below, and I'll let you know if you got them right. Please give this video a giant quacks up. And when you're out of luck in chemistry, subscribe to Duck. Keep it quacky.
No ducks, no glory.